Today I'm presenting about parameter-efficient fine-tuning and possibly pre-training as well. So a bit about me. For those who don't know, my name's Lawrence. I'm currently a master's student in the electrical engineering department. I graduated here, electrical engineering as well, best major in 2024. Um, and I'm currently doing research with Professor Lin Yang in the EC department about efficient machine learning. So like retraining, fine-tuning, inference, so on and so forth. Hello. And that's a picture of me from Sentosa Island in Singapore. But yeah. All right. So table of contents. So let's first start off with some motivation. And then I'll cover low rank adapters, which is basically like the current, I guess, golden standard of how you do fine tuning, as well as some improvements, such as quantized variance, adaptive rank allocation, gradient-free variance, and moving beyond low rank formulation, as well as covering a bit about pre-training and the current approaches to try to do efficient machine learning for pre-training. Okay. So let's get started. So as I mentioned previously, this will cover parameter efficient fine-tuning and pre-training. Thank you. Primarily, I will focus on large language models. However, the vast majority of the approaches I detail in the following slides are largely model agnostic and modality agnostic. So you could apply it towards other domains as well. It's just that large language models is probably the most well-studied domain. And most of the papers are focused towards large language models. I primarily focus on adapter-based methods, so like low rank and such, rather than prefix tuning because I'm not as familiar with prefix tuning and that kind of stuff, and because I like the math that's in adapter-based methods. Okay, so let's start with some motivation. So given the pre-trained model, commonly we would want to fine-tune it for further downstream tasks. The problem is that full fine-tuning is very expensive. So the first row here details the amount of memory you would need to fine-tune each model in full precision. And you can see that even for a 7 billion parameter model, this is 120 gigabytes, which is well outside the range of most consumer devices. And you'd have to go to servers or have your own cache of A100s to do that. So why is let me move this a little bit. So why is why is it so expensive? Well, one of the primary problems is with ADAM, which is the standard optimizer that we use these days. Basically, what it does is instead of directly using the gradients to update the weights, it computes these two moving averages of the first and second moments, and then use these to basically normalize the gradient before updating it. This is so-called like adaptive learning. The problem is you have to store these the first and second moments in memory. Because these are usually pretty small, you want to use 32-bit floats for them. 16-bit kind of is a bit tricky. So that requires an additional 8 bytes per parameter, which is a lot. For instance, for a 7 billion parameter model, this is a 56 gigabyte overhead. Okay. So then what can we do about this?
Paleo, right?
Okay. So let's move on towards low rank adapters. Okay. So we can express each of the fine-tuned weight matrices as the sum of the original weight matrix, W naught, and this the fine-tuned what the fine-tuned part adds. So that's delta W. The hypothesis that LoRA comes up with is that what if the weight updates of fine-tuning have an intrinsic low rank? If that so that means that we can parameterize it as B times A, where B and A are both rectangular matrices, where the rank is much smaller than the actual dimension of the matrix. Okay, so then what does this give us? well, then we could freeze the original weight and just simply, and we could explicitly write out these low rank adapters and explicitly just train these low rank adapters. Um, so that would basically completely remove our need for gradients as well as the first and second moments um, from the atom optimizer, sorry, which saves us about 3/4 of reduction cost. Um, and the other benefit is that there's no additional inference latency because when it comes to inference, we can explicitly compute out A times B and then add this back to W to get our new fine-tuned weight matrix. The other nice thing is that we can train different adapters for different tasks and then we can swap them. Um, so this allows us to quickly have one model, but we could we could just have to load the model plus these low rank adapters for different tasks. This is, as I mentioned previously, the standard parameter efficient method. Questions? Okay. So let's move on further. Okay. So the question is, can we reduce the memory overhead even further? Um, so now the dominant memory cost comes from frozen weight, which in LoRA is still kept in FP16. So that's 2 bytes per parameter. So the first paper, which is called QLoRA by Dimitrov et al., they just straight up quantize the frozen weight matrix. This reduces the overhead significantly. The question is, can we do this better? So this is what LoftQ does. So QLoRA just initializes A and B as standard, as A as a normal standard Gaussian, and B as a zero matrix. So this ensures that so for LoRA, the point of this is that when we initialize it, the initially the multiplication of the adapters goes to 0. So there's no initial so we initialize it from the same point as the pre-trained model. For QLoRA, what they do is they do the same thing. However, quantizing adds a bit of error. So what LoftQ does is it suggests a different initialization method that reduces this error. So how they do it is you want your initialization point to minimize the gap between their original wave matrix W and your quantized wave matrix plus these low rank adapters. So what they do is they iterate between 2 steps. They alternate between 2 steps. The first step is they quantize the weight matrix subtracted by the low rank adapters. And then the second one, they do the weight matrix subtracted by the quantized version, and then you do SVD to get low rank approximations. And you use these as your starting points for LoRA. This improves the stability in the 2-bit regime. Previously, QLoRA had some convergence issues in 2-bit. And this version converges a lot more nicely and has performance that's a lot closer to full LoRA and full fine-tuning. Another thing I'd like to point out is that Yi Xiao, and I may have covered up his name, but Yi Xiao, I worked with Yi Xiao on a bit on a couple other projects, and he's actually the third author on my paper. So what's the impact of quantization? Well, it reduces our memory overhead very significantly. So for instance, if we do 2-bit quantization of the frozen weight matrix, our memory cost for tuning 7 billion parameter model is now 4 gigabytes compared to 120 gigabytes. This is completely accessible to even GPUs as old as like a RTX 28. As a matter of fact, you can now fine tune with at 2 bits, even a 70 billion parameter model on on consumer grade hardware. So like 24 gigabytes is within the range of 4090s and 5090s. Okay, so then let's move on to the second problem. The second problem is in original LoRA, the ranks of the weight matrices are distributed, have have the same rank for each for each weight that we are fine tuning, which for original LoRA was just the multi-head attention. The question is that optimal? Clearly, it's not. So then the question becomes, if we have like a budget of memory, which corresponds to a budget of parameters, um, can we allocate this in an efficient manner to improve the performance? Then the question becomes, how do we distribute this? So what this paper proposes is that they use an importance metrics, um, which is given by the absolute value of the weight times its gradient. The idea of this is that it's a first order approximation in essence of the Taylor series of and allows you to approximate basically what happens if you zero out Wij. Actually, Tuo, who's the last philosopher who I also worked with, he very much likes this importance metric, and he uses it in a lot of his papers for all kinds of different stuff. The problem is that this gradient, this term is highly influenced by which mini batch you sample to get the gradient. So what he proposes is, what these authors propose is the so-called exponential moving average, where in essence they take the first and second moments. It's actually not the second moment. Well, in the paper they claim it's the second moment. It's not really the second moment, but in essence they have two moving averages of this importance fraction, and they multiply this, which adds stability because now with the moving average we're less dependent on the actual mini batches. Okay, so then how can we use this to adaptively allocate the rank of the matrix? So we start with, so the first thing that they do is instead of using a standard low rank A and B, they actually do a SVD like decomposition, where you have P, a diagonal matrix delta, and Q, and you use a regularizer to ensure that P and Q are orthogonal, which is a property of SVD. And then they use the aforementioned importance matrix to basically measure the importance of each rank, by just taking basically the average of the importance of each column of each column of Q, each row of K, each column of P, each row of Q, and the singular value. And then they have this budget of so using this, you can now rank the importance of each individual row, column, singular value pair in the whole entire large language model. So they create a budget of BT, where this is basically annealed from slightly higher than your target budget all the way down to your target budget. And then they pick and then they just prune the ones that aren't within the top budget of the overall large language model. This is actually, so the pretty cool thing about this is then you can visualize which weight matrices for each weight matrices, the rank associated with it, and you can see that like the more important weight matrices get allocated higher rank, where the less important weight matrices, such as for instance this one, have very low rank. And this significantly outperforms LoRA, as one would expect, because you're adaptively allocating the rank rather than fixing the rank of every parameter. Okay, so the problem is that we still have the overhead of actually holding the optimizer states for the adaptive, for the low rank adapters, which for the purposes previously we've assumed to be negligible. However, the question is, can we reduce this further? So this is what this MEM0 paper does. And what they ask is basically, can we fine tune with only forward pass? So what this would mean is that our memory overhead would be just the same as inference. And we could, what they do is effectively they sample a random direction z, and then they just perturb the weights a little bit on either side of z, and use that to create like a pseudo gradient, and just follow that pseudo gradient each time randomly picking a different z. So Sadika actually is interviewing right now to be a professor in the EC department. I talked to her. But yeah, it's a very cool paper. They come up with some theoretical proofs to show why it works, but I won't bore you with the exact math. But basically, surprisingly, this is actually very competitive with LoRA. The main reason is because we're actually not bounded by low rate structure. Because, but the reason why we don't outperform it is because this is, in essence, a zeroth order approximation of stochastic gradients, which, as we know, performs worse than atom for most stuff. Okay, so then the question becomes, can we explicitly move beyond low rank formulations? So this is what this paper Quanta proposes. Dee is actually a professor, just joined as a professor here. But basically, for certain fine-tuning data sets, which are more, shall we say, complicated, they have a higher intrinsic rank, which makes LoRA not sufficient. So the question is, can we design an efficient method to facilitate high rank updates while keeping the parameter count low? So this enables efficient fine tuning. So what they propose is something that's based off of quantum circuits. Okay, so first a little overview of quantum circuits. So in quantum, for quantum computing, we have this kind of n-qubit state, which we can denote as basically this complex vector of 2 to the n, where n is the number of, is for n qubit state. And then you can write this out as the summation of basis vectors and their weights. And basically, you can reshape this into a tensor by breaking each individual qubit up into its own value. So you get something of c to the 2 by 2 by 2 by 2 n times. So what a quantum circuit effectively is it's a matrix of size 2 to n that by 2 to the n that applies to phi. So in terms of matrix operations, it's literally just multiplication. And then there's a universal theorem in quantum computing, which is fairly important, that says that you can, for any quantum circuit, you can decompose it into 1 and 2 bit gates, where a 1-bit gate is it operating on one single qubit, and a 2-bit gate is basically operating on 2 qubits. So you can do this sequentially, and you can be shown that this can, as I said, can be decomposed into 1 and 2-bit gates. So how do we use this for fine tuning? So first thing we do is in quantum mechanics, these gates have to be unitary. And we relax that constraint and allow for, instead of 2 by 2, we allow for our arbitrary dimensions. So instead of qubits, we have what they in the paper call qubits, because it's basically d by d by d the dimension. And then we can likewise we can kind of relax we relax the unitary constraint, and instead of using a complex space, which is a bit hard to optimize, we go back to the real space and we create these kinds of 2 qubit gates, where it's literally just a matrix that multiplies along those 2 dimensions. So for instance, you can see this one is between the m and n dimension. And it's just a matrix of size, the dm by dm dn. And we can chain these together. So for instance, here down below, I've written out the explicit formulation for a 3-gate qubit circuit. You can actually do this fairly easily with eigensum in PyTorch, which is their main claim. So then we basically, instead of using a low rank adapter, we use these tensor QDIT adapters. So because we still want it to initialize equivalent to the original weight matrix, we basically we make a copy of the randomly initialized gates, and then we just subtract it. We freeze it and we subtract it. So at time zero, these two are equivalent, so we can cancel them, so we get back to our original weight matrix. And then the other nice thing is that because S is frozen, we can actually pre-compute W naught plus S. So then there's no additional overhead, and we can just merge it back into a frozen matrix of W naught prime. So what's important about this? So the nice thing about quanta is that you can have some pretty interesting theorems. The first theorem is that you can decompose each weight matrix into a finite sequence of tensors and gates and stuff. The second one is actually a little bit more important. What it says is basically you can for a group of tensor quanta operators, and each of them would rank R alpha. You can actually get a bound on the upper and lower bound on your final adapters rank. And the interesting thing about the upper bound is if R alpha, so the rank of our individual weight tensors, is equivalent to D alpha, their dimension, then it means that R is actually upper bound by D. So what it means is that if each of the tensor operators themselves are full rank, then the overall rank of your adapter will also be full rank. So this is what allows for full rank updates, even with much lower parameter counts. And the third theorem is basically what it says is that you can pull out for matrices generated from a quanta structure. Even for two matrices that you can generate, the multiplication of them two may not be in the set of matrices that you can generate. So what this means is that basically, even for near linear neural networks, we can still have a benefit of using quanta, which LoRA you can't have such a proof for LoRA. Okay, so then let me see. Okay, so then the question becomes, what about pre-training? So for pre-training, we can't assume that the original weight matrix has a low rank component. This holds for even very simple problems. For instance, linear regression, your optimal W is the pseudo inverse of your data set. And this is not necessarily going to have a low rank characteristic. At the same time, the other natural idea is, okay, what if we train it in low precision? The problem is in low precisions, you start getting exploding gradients and training becomes very unstable. This especially holds true when you quantize both the weights and the activations. So then what? So now I'm going to talk about some gradient low rank methods. So while the weight matrix itself may not be low rank, you can prove for certain structures that actually the gradient will become low rank. This holds in particular for just the up projection of a feed-forward neural network in a transformer. And then so basically what this theorem shows is that the gradient of V is exponentially more low rank than V itself in a transformer. Note that this only holds for the up projection of a feed-forward network in a transformer and doesn't hold for anything else in a transformer. But when has theory ever stopped us from actually trying? Okay, so that's what GaLORE comes up with. And basically, the key idea is that we project the gradient into a low rank subspace, and we'll swap the low rank subspaces after a certain number of steps. So it's not just optimizing along one subspace, but as shown in this picture, you switch to another one, and you switch to another one, so on and so forth. And then basically, we project this gradient into this compact space. We do atom in this compact state. So that allows our atom optimizer states to be stored to take up much less memory overhead than your overall model. And then when it comes time to do the update, we project it back into our high rank space to do the update. Okay. So then the question becomes, how do we choose the subspace? What GaLORE comes up with is basically they just do after every t steps, they just do an SVD decomposition of the gradient. And then you get USV, and then PT is you just clip the first R rows of U. The really cool thing about this is that what it shows is that you can pre-train a 7 billion parameter model on a 49. So what this now does is it makes pre-training accessible to the general consumer grade hardware. They actually come up with additional improvement called QLoRA, where they quantize some stuff, and this reduces it even further and makes pre-training even more accessible. But then the question becomes, is this kind of subspace sampling based off of the SVD optimal? Provably, actually, it's not. And what people have found in practice is actually a random-based subsampling is more effective because there is a danger that that this PT will get frozen by the gradient. And so instead of swapping between subspaces, you just stuck to the same subspace and optimize it down that subspace, which obviously is not optimal. So what I3S does by Hao Chen is that they do subspace selection. And basically, instead of just explicitly taking the highest, so selecting your subspace based off of those with the highest singular value, you randomly sample based off of the singular values, and they show that they get a significant improvement compared to standard GaLORE. Hao Chen did his master's here at UCLA. He was my lab mate, actually. And Lin is on the paper. And yeah, that's that. Sorry, I speed ran that. But yeah, the papers presented here are just basically an overall slice of the field. I didn't cover a couple things such as sparsity-based methods because those have some other constraints, as well as there's now some quantized or like low precision pre-training methods that are also being proposed these days. I'm looking for a collaboration ideas to pursue. Feel free to reach out to me. Here's my email, X. But yeah, that's that.
What?
Did you have a question?
Sorry.
Oh, okay. Jerry.
So I think that was your first slide on the board.
Uh-huh.
Talked about projecting.
Yes.
Projecting. So I was curious, does projecting it cause any loss of information?
Yes, because the theory is basically if you're doing a full rank update, you have your full entire full. But if it's low rank, you're basically so in like a 2D space, if we were to imagine it, if it's a full rank update, we can do the full 2D space. But if we're doing a projected version, then we're basically projecting it onto a line. So we can only optimize along that line. And we're just hoping that that line changes direction between steps because of this gradient thing. And that's actually the key thing that I3S tries to solve is basically GaLORE sometimes you will just freeze it along a line and then it'll just be optimizing along that line over and over again. So by doing random sampling, you push it off of that line. And then you push it into different subspaces. That's why it's better. But yeah.
So we kind of don't need to feel all the information.
So the inference is still done in full rank. So for pass is done as full rank. The primary goal benefit is that basically the is that the low rank is that I hate you. It's that is um that Atom is done in low rank. So then your optimizer states, so your first and second moments, those are no longer shaped D by D, but like R by D, where R is a lot smaller. And then so that saves you. So that basically moves the atoms overhead from a quadratic overhead to a linear overhead or near linear. But yeah.
They do this to the entire transformer regardless.
Yeah. Mhm.
Okay. Could you cover the what was it called again? The quanta adapters slides?
You can go talk to D about this. Actually, no, D will probably yell at you, but yeah.
Fine.
Um,
Yeah, I'm just slightly confused about the shape of the adapters.
so the shape of the adapters are really just so if we have three if our quanta consists of three qubits, then you have basically uh you you decompose your you reshape your activations into a from a one D vector to a three D array, right? And then you have um your first gate in a sense operates between your second and third, and then as shown here, your second one operates between your first and second. No, sorry, first and third, and then your final one operates between your first and second.
And these all represented as like matrices.
As matrices, yeah. So let's do a simple example. So if D is let's say 8, then we do this decomposition 2 by 2 by 2 matrix. Right. So first one is 4 by 4 matrix. Second one's 4 by 4. The third one's 4 by 4.
And you said so you reshape like the activations for this, right?
Yeah.
What are you do you have like I guess before this, do you have like some sort of like MLP that will output like this qubit shape?
You no. So you take you just reshape it.
Oh, I see.
You physically reshape it. Which the problem with this is actually you're screwing up with how the memory is arranged actually in the GPU, and you have to do a lot of shuffling. So that's why this is actually that used in modern stuff. But yeah. I see.
I might have missed this. Can you explain why people started doing low rank on the gradient rather?
Because sort of the matrix itself is full rank in most cases, right? You can't really enforce low rank without massively reducing your performance of your model.
Oh, okay.
But what they have some theorems. This is like theoretical machine learning, but no, so not this one. There there are some theorems for like certain specific classes of neural networks. You can prove that the gradient will become lower.
So they just said, okay,
So
let's just do it all.
yes, but you can't prove that for a transformer. But they're like, all right, why the hell not? Let's try it. It's working. Yeah. But you know, this is still like academic work. So they haven't really scaled it up to like proper, 100 billion parameter models. But within like 7 billion parameter models, it seems to be. But yeah.
So, oh, sorry, did you have another? I was just gonna say, like, how recent is GaLORE?
GaLORE was, I believe, 2024.
Oh, okay, so
Yeah. I3 because Hao Chen was working on I3S for summer and fall of last year. And GaLORE, if I recall correctly, that's like just came out by that point. But yeah. Yeah. Go ahead.
So I was wondering, there was a slide you're talking about like a forward propagation, or like you didn't use back propagation.
Yeah, the mem zero paper by Sadika.
Was that actually like successful? You just find
Yes, surprisingly, yes. It's actually pretty. It's comparable okay. It's comparable to LoRA. Of course, in the actual paper itself, they'll move the numbers a little bit so that it's improves over LoRA, but basically it's around the same points as LoRA. The main benefit is, of course, that this actually allows for high rank updates. because we're not explicitly parameterizing the adaptive part is the low rank.
Wait, can you explain that? Because some of those words I don't fully understand.
Okay. So
like, what does backpropagation do? Like, what does this do that backpropagation do?
So backprop is you backprop is you take the derivative, right?
Yeah.
And then so for LoRA, you are constraining the weight, the final fine-tuned weight matrix to be of the shape W naught plus a low rate delta, right? Because we are explicitly parameterizing delta W as B times A. So we can't have a high rank update on W. MEM0 just directly updates W. It skips the adaptive part. So this allows for full rank updates.
This sort of went over my head. I'm just gonna have to do some research on my own.
Basically, yeah, so basically the key thing is MEM0 doesn't have a low rank, doesn't have a low rank explicit formulation. It's directly updating W. We can't directly update W for fine tuning because that's really expensive because we have to store those additional gradients and optimizer states. And that's actually the primary overhead compared to actual the model cost itself. So what MEM0 does is it says, screw the gradient, screw the optimizer states. We will just do a 0th order approximation of stochastic gradient descent on the on the weight matrix itself.
And I guess what was it? So LoRA matrices have a lot less parameters. They're easier to store. And that means that updating them also takes up less parameters, right? But if you have to represent something as like B and A are both lower matrices, right? If you have to represent something as B times A, although it's like quicker to update, and that's why they use it. That's the point of LoRA is that you can update it quickly. It has a limit on the amount of information it's actually store.
Yes,
I guess.
exactly.
So if you are able to update a full
No,
range
it's not.
matrix,
I
instead of what these lowering matrices, you can get theoretically like better performance.
because
And a lot of the papers here
additional benefit is that L is
formulation, which is like
yes, but
explicitly the multiplication of two low-res matrices. The MEM0 doesn't use that, and it's kind of like a separate thing that just says, hey, instead of using backprop, let's just use an approximation of it without the low rank. So it doesn't
store that much.
You kind of literally
yes,
because the approximation, like instead of trying to reduce the parameters, it's reducing how expensive it is.
No, it doesn't work actually. Only for fine tuning.
Yeah, makes it more sense.
What? I imagine you would like approximately.
Okay, Thomas, what?
What's the rank of a matrix? Wait, I don't know. No, I ironically don't know.
Okay. So okay. Departmental scholar, electrical engineering, top like 2 in our class, right here. My God, Thomas. Even the freshmen think they. Okay.
Freshmen are right. I am stupid.
Okay. Yeah, president of the EE Honor Society, right? What do you talk to with Ken Yang? On a daily basis?
Don't worry about it.
What does Ken Yang think of you?
No, but ironically, what is the rank of a matrix?
Okay. Nathan, do you want to explain this?
You got this.
God.
How big is the matrix? Doesn't matter.
Doesn't matter.
It's just
It's just basically rank of the matrix is in the mathematical sense, is basically you can express is what
Are you?
watch it out. Watch it out. Watch it out. Okay, so basically, your rank in essence is using how many orthogonal vectors you have to scan through that matrix in either your rows or column space. And a low rank matrix basically means that you can express the matrix as two rectangular matrices of much smaller than the original mesh, which allows us to say parameters.
Okay.
I thought you were gonna go into like the more lineage perspective.
You forgot remember now. All I remember is make multiplication SVD. But yeah.
Well, I think I'm like I'm in like linear algebra 3A, so I'm just trying to learn this on my own. But like if you have like rows that are linearly dependent, then it like reduces the rank in a sense.
Yeah.
Okay.
So say that you have a n by n matrix status. It doesn't actually matter. So there's like a theorem in linear algebra that says that the rank of the rows is actually the rank of the columns. So that's why they just use rank as a column rank versus row rank. And what you do is you just do Gauss-Jordan elimination, and you can find out how many columns to get to zero. Those columns are not part of the rank of matrix. So how many linearly independent columns you have is the rank of matrix. Okay, for the transformation. Yeah, essentially. You take the minimum of the row rank and the column rank, then you actually find that the bounding works out to that the row rank and the column rank are the same thing. So just call it rank. All right. Then no one cares yet. Call it specifically something.
And you can also do SGD in practice together. Because really actually they aren't low rank. Like you if you look at the actual weight updates, with Gauss-Jordan you can't actually get that far. So if you look at that singular value decomposition, if you look at singular values, they drop off basically. That's very low. It's low rank, it's confusing. But yeah.
So we talked about like the quantum circuits, but I don't understand how that actually plays into the like novelty of this method. So is the quantum circuits inspiring like the decomposition after reshaping?
Yeah, and then the multiplying. Yeah. Basically, the decomposition after reshaping, and then this kind of you basically you're doing matrix multiplication along two selected dimensions after you reshape it and dimension space. And you can prove that results in full rank of data, even with this time.
And because it's either 1-bit or 2-bit gates, this is like a really sparse.
Okay, so because they relaxed the unitary constraint, you can now express 1-bit gates. You can basically, if you have a 2-bit and then like a 1-bit joining, you can just combine them together into 2 gate.
Certainly.
So you'll notice that they don't have any actual in the thing. You don't actually have any 1-bit gates. Like for instance, so this is like actual quantum circuit, right? These are like 1-bit gates.
Yeah.
Here you don't have it. They do this, so they don't actually explicitly write out 1-bit gates because they've relaxed the unitary constraint.
So you just kind of add it in?
Yeah, you can
combine it.
Yeah, with the two, yeah.
But the reason why this uses a bunch of less parameters is because you're only like messing with like 2 gates at a time.
Yeah.
So it's like sparse,
It's in so you can explicitly, so for instance, this explicitly writes out your update in terms of like the actual matrix multiplication between gates,
Yeah.
that isn't actually sparse. So it's not sparse in like the traditional sense of sparsity, where like if you look at it, there's certain zeros. Yeah. It's sparse in the sense that like if you do like a very simple example. So if x is of like 40996, right? Standard stuff. If you decompose it into 3 dimensions, that's two sort of 16, right? It's 16 by 16 by 16.
I'm not doing
If
that.
someone can do the math, don't turn back. That's right, right? So then if it's 16 by 16 by 16, each of these is 16 squared parameters. You have 3 of them. So that's so compared to a full rank update, which would be 40996 squared. It's now 16 squared times 3. And that's voila. Wow. Huge. But yeah. Okay. If there's no more questions, then yeah, I guess that's that.
I guess
Yeah.
I have
Go ahead.
just 2 more questions.
sure.
Is so regarding the subspace switching for the car, how are they choosing the subspace exactly?
They do SVD on the gradient, and then you just click
Okay,
your P.
so like so the dimensional like highest like variance is the one they're choosing.
Yeah.
Okay, so they're choosing high. So how come the one with the highest variance, like the top 3 highest variances, those dimensions like
Different.
don't do as well as just randomly sampling?
Because so then the question becomes which are the top deep dimensions, and that gets basically messy. After some time.
I see. After some.
Yeah, and then so then you're just optimizing along one line, and you're going back and forth along that line, and you want to force it out. So that's what I3 does. Is that basically you can force it out.
Is the IQS random sample?
It's
not just like it's not like a uniform distribution. It like
so actually uniform works just as well.
Oh, sure.
The problem is you can't have any proofs for uniform distributions. You can have a proof if you're weighting it by the SVD. So that's why they did that. So you can have actual proof. But yeah.
So it's like the way that they do this is like they calculate the SVD or they randomly sample. They go into the subspace, they perform atom, roll back to the original space and update the weights.
Yeah.
And they repeat that.
So yeah, but the subspace you choose because you don't want to do SVD every iteration, so that's really slow.
Okay.
So they'll fix it for a certain number of iterations and then go back and update. So that's why like in this picture you can see for these steps it's all fixed and then they switch in their subspace.
Oh, I see. So in the beginning you're actually still within the normal like original space. Do you stay in the original space from the very start?
No, you immediately start projecting because otherwise then your like peak memory usage would still be equivalent to your overall. But yeah.
Right. Makes sense. Are you guys got any other questions?
Go ahead.
What's your favorite flavor ice cream?
Chocolate chip.
Chocolate?
Yeah.
Like
Yes.
chocolate with chocolate chip?
Yes. Chocolate.
Do you like the chunks or like?
Chips.
What's your favorite
Oh my
Ben and Jerry.
I haven't seen Ben and Jerry's ice cream. I actually haven't had ice cream in quite a while. Well,
Ice cream? Ice
I'm
cream?
probably gonna go on a run, but
It's 90 degrees outside, guys.
You're gonna like burn.
it's fine.
You can get crispy.
That is true.
Yeah.
It's really hot.
But I also have to get ready.
Oh, yeah.
When's the marathon?
Tyler.
No, sorry, it's my bad. I should be okay.
When's the marathon?
I'm probably not gonna run the one on May 18th because there's no way I'm ready for that. But I'll find one in Seattle. Go ahead.